Right now, as you are watching this, a telescope floating 1 million miles from Earth is staring at a frozen rock nearly 4 billion miles away. And what it is finding there is the exact outcome that mission planners at NASA once feared most for decades. This is not a fun space fact. This is a quiet warning shot from the edge of the solar system. Tonight, we are going to walk through what James Webb just saw on Pluto, why scientists are quietly saying, "I told you so," and what it means for a world we thought would stay frozen solid forever. Before we go any further, hit subscribe and turn on the bell so you never miss the next deep dive like this one. And drop a quick comment with just your country and city, because I want to see how global this story really goes. Back to it. In 2015, NASA's New Horizons spacecraft flew past Pluto at more than 30,000 miles per hour and gave humanity its very first close-up look. That flyby changed everything. It revealed a heart-shaped ice plain the size of Texas, mountain ranges made of water ice, slow glaciers of frozen nitrogen, and a thin blue atmosphere floating above the surface like a halo. For a few years, the story felt triumphant. We had finally reached the forgotten ninth world, and it was alive, in its own quiet way. Then the questions started stacking up. Scientists noticed the upper atmosphere of Pluto was about 30 degrees Celsius colder than every computer model on Earth predicted. In plain language, the sky above Pluto was behaving like a freezer that should not have been running that cold. Paper after paper tried to explain the missing heat. Some pointed to the chemistry, some pointed to the tilt of the planet, some said it was a measurement error. Nobody could nail it down, and the leading fear inside the mission teams was the worst case. That fear was simple. The nitrogen gas that holds the whole atmosphere together would start freezing onto the surface. The thin blue haze would collapse, and Pluto would slip from a world with weather into a quiet ball of ice. Back then, NASA warned that moment could arrive near the year 2030. Now jump to today. The James Webb Space Telescope is finally powerful enough to look at Pluto in mid-infrared light, the kind of light our eyes cannot see, but which carries the signature of heat, dust, and chemistry. In 2022 and 2023, Webb pointed its MIRI instrument at the Pluto system 9 separate times. The dataset came down through 2024. The first peer-reviewed papers landed in early 2025, and the most important one appeared in the journal Nature Astronomy on June 2, 2025. It confirmed the worst fear with eerie precision. Pluto's haze is real, it is thick, and it is actively freezing its own atmosphere from the inside. Here is the science in words a 7-year-old could follow. Imagine a cold room with a thin fog hovering just above the floor. Sprinkle a layer of dark dust through that fog. The dust catches the tiny amount of light that makes it into the room, soaks it up, and then shoots that heat outward in every direction. Some of it goes down toward the floor, some of it goes up and escapes into space. Because so much heat escapes upward, the fog ends up colder than it should be. That is exactly what is happening on Pluto, except the floor is a sheet of nitrogen ice, and the room is the entire planet. The haze is Pluto's thermostat, and the dial is stuck on cold. To put numbers on this, Pluto sits about 3.7 billion miles from the Sun. That is roughly 40 times farther out than Earth. The sunlight that reaches Pluto is more than 1,000 times weaker than what we get at home. When MIRI measured the planet at wavelengths between 15 and 25 microns, it found a glowing signature from a hazy layer so cold that no clean gas model could explain it. The haze particles themselves sat near minus 203 degrees Celsius, but the air above the haze was even colder, near minus 230, matching the puzzling ground-based measurements taken over the last 3 decades. That is a real gap. That is the old mystery finally answered. This is not a small correction. This is a rewrite of how a whole world's weather works. The haze particles, made from nitrogen, methane, and carbon monoxide reacting to faint sunlight, are doing the same job as soot in a smokestack. They trap heat in one spot and radiate it out in another. On Earth, that effect warms the surrounding air. On Pluto, because the surrounding air is so thin and cold, the same physics ends up cooling it. Until Webb, no one had proven this in real data. Now we have, with paper and peer review behind it. Here is where the human stakes show up. The lead theorist behind this idea is a planetary scientist named Shi Zhang at the University of California, Santa Cruz. In 2017, 2 years after the New Horizons flyby, Zhang published a paper arguing exactly this, that Pluto's haze does the temperature control, not the gas itself. At the time, he called it a crazy idea, and his peers openly questioned it on conference panels. His prediction was bold. If he was right, Pluto would have to glow strongly in mid-infrared light. For 8 years, that prediction sat on a shelf, because no telescope on Earth or in space could test it. Then, on Christmas Day 2021, NASA launched James Webb, and the test became possible. The team that ran the test was led by Tanguy Bertrand and Emmanuel Lelouch at the Paris Observatory in France, with Zhang's group contributing the theoretical models. Zhang's former PhD student Linfeng Wan also co-authored the analysis. They pulled Pluto and its moon Charon apart in the data, measured them separately at 18, 21, and 25 microns, and matched the result against Zhang's old prediction. The fit was clean. Zhang told reporters, "We were really proud because it confirmed our prediction. In planetary science, it is not common to have a hypothesis confirmed so quickly, within just a few years, so we feel pretty lucky and very excited." That is a real quote from a real scientist, watching his toughest gamble pay off inside a single decade. Now I want to stop for a second and be honest with you about what this paper is not saying, because the internet is moving fast right now and a few versions of this story have already gone viral in the wrong direction. Some posts claim Webb proved Pluto's atmosphere is gone forever and that the planet is already a dead rock. That is not what the paper says. What the paper says is that the haze is cooling the upper atmosphere faster than anyone expected. It does not say the air vanished overnight. It does not say the surface froze. It does not say tomorrow is the end. Some clips have stretched the headline for clicks. The truth is more careful. The truth is this: the cooling is real, the prediction matched, and the collapse timeline now looks closer than the optimistic models had hoped. That is the real fear, and it is enough on its own to pay attention to. Let's talk about the bigger picture, because this is where the story gets strange. Pluto's atmosphere is held up by vapor pressure, which is a fancy way of saying the cold on the surface is not quite cold enough for the nitrogen ice to stay rock solid, so a little of it keeps evaporating into gas every season. That balance is fragile. Right now, Pluto is moving away from the Sun in its 248-year oval orbit. As it slides farther, the surface gets colder, the nitrogen ice holds tighter, and less gas escapes into the air each year. The worry is not a single bang. It is a slow leak. The air thins out over decades, the haze thins out with it, and eventually even the small amount of escaping gas is too weak to keep the blue sky aloft. In plain words, Pluto is slowly losing its breath, and no one alive today will see the final exhale, but the countdown has already begun. Some viewers are now asking the scariest quiet question in the back of their head: is this happening anywhere closer to home? The honest answer is no, and here is why. Earth's atmosphere is held up by gravity and kept warm by a giant magnetic field and a hot core. Mars lost most of its air because it has no magnetic shield, not because it got too cold. Pluto's collapse is its own special problem at the edge of the solar system. The only other places that even share the same recipe are Saturn's moon Titan and Neptune's moon Triton. Both of those worlds are hazy and nitrogen-rich, so this finding does not threaten Earth directly. It does, however, teach us how small, icy worlds live and die, which matters because most of the worlds we will ever discover around other stars are small, cold, and icy, not big and warm like ours. Here is another angle that almost no one is talking about yet, and it is one of the most chilling parts of the data. The haze is not only cooling Pluto's air, some of it is actually leaving the planet and falling onto Charon, Pluto's big moon. The molecules drift across the nearly 12,000-mile gap, then freeze on Charon's north and south poles, staining those regions a rusty reddish-brown. In the Webb dataset, Charon's poles show a thermal signature that matches freshly deposited material, not old surface ice. In plain language, Pluto is raining down on its own moon. We have never seen that anywhere else in the solar system. It is quiet, it is slow, and it is happening right now. To put that in everyday terms, imagine standing on a beach and watching sand drift from one island onto another across a wide bay. Now imagine the sand is made of frozen nitrogen, and the bay is wider than the distance from New York to Sydney. That is what is happening above Pluto, every rotation, every season. The haze leaves, the atmosphere thins, the surface cools further, and a little more material rains onto Charon. It is a closed loop, and each loop tightens the next one. So how worried should you actually be? On a scale from 1 to 10, where 1 is a fun telescope update and 10 is a planet-wide catastrophe overnight, this is about a 6. It is real, it is confirmed, and the science matches the worst-case timeline from the early models. It is also still decades away from running out completely. Pluto will not lose its entire atmosphere next week or next year. We are watching something begin, not end. The collapse window runs from now through the late 2030s, with the lowest air pressure moment expected somewhere in the middle of this century. The point is not panic. The point is that the fear the mission planners had back in 2015, the one they whispered about in side conversations at conferences, has now matched the data. That matters. Now, what can you actually do with this information? I know that sounds like a strange question for a story about a world 4 billion miles away, but bear with me. There are 3 practical things. First, support the missions. James Webb was a once-in-a-generation bet by NASA, the European Space Agency, and the Canadian Space Agency. It is funded year by year, and every story like this one that shows real public interest helps justify the next great observatory. Second, follow the lead researchers. Tanguy Bertrand, Emmanuel Lelouch, and Shi Zhang all post their work on open archives. You can read the actual papers in Nature Astronomy and Astronomy and Astrophysics with one click on your phone. Science is no longer locked behind university walls. Third, learn the difference between a confirmed result and a viral screenshot. If you remember that habit, you will never get played by space hype again. If this story actually changed how you think about our solar system, smash that like button so the algorithm shows it to more people who care about real science, not recycled clickbait. Comment below with the country you are watching from, because I promised at the start I would track the global footprint of this story, and I read every reply. And if you have not subscribed yet, this is a good moment, because the next paper drop on Triton is going to make this one look like a warm-up act. Let's keep moving. Here's the part of the script where I want to slow down and answer the question a lot of you typed into Google to find this video. Is this connected to the climate story on Earth? No, not directly. Pluto's atmosphere is collapsing because it is getting colder as it drifts farther from the sun, not hotter. Earth's climate story is dominated by greenhouse gases trapping heat, which is the opposite physics. The only shared thread is that both stories involve a thin layer of air, and both stories teach us how fragile a thin layer of air is when the chemistry and the sunlight shift. In that sense, Pluto is a mirror held up to our own planet. It shows what happens when the energy balance goes one way for a very long time, and the sky thins out without anyone sounding an alarm. Now let me take you back to the numbers, because the human brain needs concrete anchors to take a story seriously. The Pluto atmosphere, measured by Webb in 2025, works out to about 10 microbars at the surface. That is roughly 1/10,000th of the air pressure on Earth. For comparison, the air pressure on the summit of Mount Everest is around 330 millibars, which is roughly 33,000 times thicker than Pluto's entire sky. So when we say Pluto has an atmosphere, what we really mean is that Pluto has a thin veil of gas you could blow away with one strong breath. And still, that veil has seasons, hazes, winds, and a chemistry stack that took the best telescope humans ever built to finally understand. Another anchor you can hold on to, the temperature gap that Webb just confirmed. The upper atmosphere is roughly 30 degrees Celsius colder than models predicted. To a kid sitting in a classroom, that is like opening a freezer and finding it 30 degrees colder than the dial says it should be. It is not a rounding error. It is the freezer actually breaking its own rule. That is why this paper matters. That is why every planetary scientist who studies outer solar system worlds stopped scrolling and read the result twice. The most surprising number to me, and the one I think will be talked about in textbooks a decade from now, is this. The haze layer is not a thin mist. It contains more than 20 distinct stacked layers, almost like the pages of a book. Webb separated them in the spectrum. Each layer has a slightly different temperature and a slightly different chemical recipe. 20 layers in an atmosphere thinner than the air a human exhales. That is wild. That is not what any model put into a textbook 10 years ago. That is brand new, and it is sitting in the Open Data Archive right now, free to download. There is a quieter idea in this data that I want to share before we move on. If haze can dominate the energy balance of an atmosphere, then a lot of our thinking about exoplanets, the worlds we are finding around other stars, might be off. Many of those worlds sit in the cold zones where hazes are common. If haze controls their temperatures the same way it controls Pluto's, then habitability calculations written 5 years ago may need serious revision. This is not a headline grabber, but it is the kind of slow, real shift in science that changes the field. Pluto is teaching us how to read atmospheres we have not even discovered yet. Quick CTA beat right here. If this is the kind of real science story you actually want more of, drop the word haze in the comments, and I will pin a thread with all the source papers linked below this video. That kind of call to action helps the channel reach people who actually care, so do not skip it. Back to the deep dive. Let's bring in something easy to picture. Think of 20 pancakes stacked on a plate, but each pancake is made of haze instead of batter, and each one sits at a different altitude. The bottom pancake touches the nitrogen ice. The top pancake floats near where space begins. Webb just measured each pancake separately. That is the kind of detail no other telescope in history has ever pulled out of Pluto. A dot that looks like a single smudge in old data turns out to be a stack of chemistry, each layer reacting to its own slice of the faint sunlight. Pluto is not a simple dot anymore. It is a layered cake of cold. Before we go further, let's talk about how this fits into the bigger arc of Pluto science, because it is bigger than one paper. In 1988, astronomers watched Pluto pass in front of a distant star and measured the way starlight bent through its atmosphere. That was the first real proof it had any air at all. In 2015, New Horizons flew past and showed mountains of ice, a heart-shaped plain, and a thin blue sky. Now, in 2025, Webb has zoomed in on the chemistry and the temperature. Each step has been 10 times more powerful than the last. Each step has rewritten the picture. The lesson here is that worlds never stop surprising us. They just wait for better eyes. Let's also talk about New Horizons' 9-year journey for a moment, because the context matters. The spacecraft launched in January 2006, the same year Pluto lost its planet status. It crossed 3 billion miles of empty space, slept through most of the trip to save power, and only woke up for its close encounter in July 2015. The pictures it returned during a single 90-minute flyby became the most downloaded images in NASA history at the time. Pluto went from being a blurry dot to a real world in one afternoon. 10 years later, the telescope that finally studied its air in mid-infrared is orbiting a point called L2, 1 million miles from Earth. The chain of human patience that got us here spans almost half a century. That is worth a pause. Here is something a lot of viewers message me about, and it deserves an honest answer. Is Pluto really a planet? The official answer from the International Astronomical Union is no. Back in 2006, Pluto was reclassified as a dwarf world because it did not clear its orbit of other debris. That decision is still debated by scientists, and it does not change the science. A dwarf world with an atmosphere and weather is still a world we should care about. A world that holds clues to how planets live, age, and quietly fade. Real talk moment. Some of you watching right now remember when Pluto was downgraded. You were told the solar system had 8 planets and that was that. The new Webb paper is a quiet rebuttal. Pluto is still changing, still moving, still losing its air. Declassify it all you want. Physics does not care about committee votes. Pluto is doing things in real time, and we are watching those things with a telescope that cost $10 billion to build and launch. One more honest beat before we move forward. Some of the exact collapse year predictions, including the famous 2030 number, came from older models that did not include haze cooling. Once you fold haze cooling into the equation, the freeze-out window shifts a bit. Some models now push the lowest pressure moment closer to the 2040s. Other models hold the 2030s line. Nobody has the final answer, and that is not a weakness of the science, it is the field being honest. The next batch of Webb data, scheduled for the next Pluto observing season, will tighten these numbers. Until then, treat any single year as a rough estimate, not a calendar invitation. I want to take a moment to give credit where it belongs in this story. The New Horizons mission was led by the Applied Physics Laboratory at Johns Hopkins. The James Webb mission is led by NASA Goddard, with major instruments contributed by the European Space Agency. The Pluto paper that triggered this whole moment was written by scientists in Paris and Santa Cruz who collaborated across an ocean. Science like this is global, expensive, slow, and easy to take for granted. When you see an article about a world 4 billion miles away, remember that thousands of people built the tools that made it possible. That is worth pausing on. Let's also look at how this finding changes the way we think about seasons on Pluto, because Pluto has seasons far stranger than ours. A single Pluto year lasts 248 Earth years. That means each region of Pluto experiences one long, slow summer and one long, slow winter in its lifetime. During the long summer part of the orbit, more nitrogen evaporates and the atmosphere puffs up. During the long winter part, the air freezes back down. Pluto right now is sliding into its most distant stretch from the Sun. That is the worst-case stretch. That is when the collapse is expected. So the Webb data is not just confirming a theory. It is also catching Pluto at exactly the wrong season in its long calendar. Here is the everyday anchor. If Pluto's year were a clock face, we are watching it somewhere around the 5 o'clock mark on the way to midnight. The atmosphere is still here. It is just thinner than it was at noon. By midnight, around the late 21st century, models say the air may disappear almost entirely for a while, before Pluto slowly swings back toward the Sun and the cycle starts again. That swing back is real. Pluto is not doomed forever. It is just in a quiet phase right now. That is a key detail the viral clips often leave out. Here is a thought experiment that helped me wrap my head around Pluto's haze, and I want to share it with you. Imagine pulling a thin wool sweater over a small flashlight in a dark room. The sweater catches the light and spreads it out as a soft glow. The bulb does not get hotter. The room does not get colder. The glow just goes everywhere. That is the haze doing its job above Pluto. Only instead of dumping the glow back into the room, the haze dumps most of it out into space, so the air around the haze stays cold. It is a one-way mirror made of tiny soot particles, and it took the most powerful space telescope humans ever flew to finally see it work. That thought experiment is the whole physics story in one picture. I want to address one more thing before we close. A few viewers have messaged asking if this could change future missions to Pluto. The short answer is yes, in a positive way. There is a growing conversation about a proposed Pluto orbiter, sometimes called the Persephone mission concept, that would launch in the late 2030s. If the haze cooling is real, the orbiter design has to account for an atmosphere that may be thinner than early ride-along designs expected. It may also get to sample the haze chemistry directly, instead of guessing from a distance. This discovery makes the case for that mission stronger, not weaker, and it gives planners a real reason to bring new instruments on board. Let's also talk about what is coming next, because the Webb team is not done with Pluto. There are follow-up observation windows already approved for 2026 and beyond. Those windows will look at how the haze shifts as Pluto moves deeper into the cold stretch of its orbit. If the cooling rates match the 2017 prediction, we are in the worst-case scenario. If the cooling rates slow, the timeline stretches. Either way, we will know more in the next 3 years than we have known in the last 30, simply because we finally have the right tool. Let's swing back to Titan and Triton for a moment, because the same haze physics probably applies there too. Titan has a thick, soupy nitrogen atmosphere and rivers of liquid methane on its surface. Webb has already detected the same cooling haze signature there. Triton orbits Neptune backwards and has geysers of nitrogen shooting out of its south pole. If haze cooling is part of Triton's weather too, those geysers may weaken as Triton moves through its long season. These are real predictions, not fairy tales, and they will be testable in the next round of Webb time. Let's do something practical right now. If you want to follow this story yourself, you can do 3 things without any special equipment. First, sign up for email alerts at the Nature Astronomy Journal website so the next Pluto paper lands in your inbox the day it is published. Second, follow Xi Zhang, Tanguy Bertrand, and Emmanuel Lelouch on the free archive site archive.org, where scientists post their papers before peer review. Third, bookmark the James Webb Space Telescope public image gallery at the official NASA website. New images drop every week. Many of them are public domain, and you can use them in school projects or share them freely with friends who still think Pluto is just a cartoon dog. Which brings us to the bigger question this story forces every curious mind to face. Are we alone in this kind of place? If a small, cold world can hold a sky for billions of years, then nitrogen haze chemistry is not rare. It is a universal recipe. Anywhere in the galaxy where a small, icy world gets enough starlight to drive chemistry, the same haze probably forms. In other words, every cold exoplanet we are now finding with Webb and ground-based giants may have its own quiet version of Pluto's blue halo, slowly fading. That thought reframes the whole conversation. Pluto stops being a lonely rock at the edge of our maps. It becomes a template for a class of worlds we have not yet seen up close. This is the kind of science that makes astronomy feel less like a museum and more like a frontier. And the discoveries are landing right now in real time while you and I are talking. Let's also pull in one more honest detail, because trust matters more than hype. The exact haze temperature the team measured sits about 30 degrees below the clean gas prediction, but the error bars on that number are still around 5 to 10 degrees. The team's paper says the gap is significant beyond doubt, but it also notes more observations will pin the number down tighter. So if you see another post tomorrow claiming the gap is 40 degrees, treat it as marketing. The real number is in the published paper, linked in the description. If you want to be the smartest person in your group chat about this story, read that paper, even just the abstract. 10 minutes of reading will beat 10 hours of scrolling. Before we close, a final, honest sentence. The bottom line is this. The haze on Pluto is real. The haze is cold. The haze is freezing the sky. And the timeline for the air to finally collapse has moved closer to today than anyone hoped when New Horizons flew past. The worst case that old mission planners whispered about in conference hallways is now the working scenario, not a fringe idea. That is the news. The lesson here is not to be scared of Pluto. The lesson is to be honest about how long a world can keep its sky and how fast the right chemistry can take it away. We talk about climate change on Earth as if it only happens here. Pluto is reminding us, in the quietest possible way, that atmospheres end. They do not end with a bang, they end with a slow exhale, thinning for decades until one day the blue halo disappears and only the ice remains. Wake up to that, and you start to understand why a frozen rock at the edge of the solar system matters to every single one of us watching. If you made it this far, you are clearly the kind of person who wants real science instead of recycled hype. Share this video with one friend who only watches car videos or cooking videos and see what happens when they get hit with Pluto on their feed. Plant one seed. Then drop a single number between 1 and 10 in the comments, predicting how much of Pluto's sky will still be there in the year 2050. I will read every guess and reply to a bunch of them directly, and your answer will help me write the next chapter of this story. Thank you for staying with me all the way to the end. You are the kind of viewer who makes this channel worth building. Subscribe if you have not, turn on notifications, and come back in a week or two when the next deep space drop lands. Until then, stay curious, look up often, and remember that the edge of the solar system is a very interesting place to keep an eye on.